Hi everyone, welcome you all back. In this video we are going to see the heat exchangers. First we will see the classification and introduction for the heat exchanger. In the next video we will solve some problems on heat exchangers. Okay, so now what is heat exchanger? So whenever a heat is exchanged between two mediums, that is from a liquid to a liquid or from a liquid to solid, then the equipment which is equipped there, it is called as heat exchangers. So here the definition is heat exchanger is a device which effectively exchange the heat from hot fluid to cold fluid. Okay, so heat exchanger finds the application in various processes like refrigerating, air conditioning systems, food processing systems, chemical reactions, aerospace applications. Then the next thing we are going to see types of heat exchangers. The types of heat exchangers. The heat exchangers are classified on the basis of various parameters, right? So first one is nature of heat exchange process. Second one is relative to the direction of fluid motion. Third one is design and constructional features. Fourth one is physical state of the fluid. So under this category, the heat exchangers are classified into number of types. Okay, so now let me take the first one, nature of heat exchange process. In nature of heat exchange process, there are two types of heat exchangers. That is, the heat exchangers are classified into two different types. First one, direct contact heat exchangers. Second one, indirect contact heat exchangers. So in the first one, in direct contact heat exchangers, the fluids which are going to exchange the heat, the two fluids will be in direct contact to each other, or by directly it is mixed together in order to exchange the heat in between them. So these are all called as direct contact heat exchanger. For example, open feed water heater and cooling towers are called as direct contact heat exchangers. Second one is indirect contact heat exchangers. In this type, this is classified into regenerators and recuperators. This recuperator can be called as surface heat exchangers. First thing, recuperators. In this type, the fluids do not come in direct contact with each other, and these two fluids are separated by a wall. The wall may be a simple wall or a complex one, maybe a composite wall or plain wall condition, plain wall. So as I already told you, this most common type of heat exchanger is called as surface heat exchangers. Also, it is constructed with large heat transfer surface area. Once the heat transfer surface area is large, then the heat exchanger efficiency will also be large. So radiator and economizers are called as the recuperators. Second one is regenerators. In this type heat exchangers, some space is alternatively occupied by hot and cold fluids between, it will be like that. Chamber will be like that, shell will be like that. So here the hot fluid is filled, here the cold fluid is filled, again here the hot fluid is filled, here cold fluid filled, here hot fluid filled. Because of the alternative arrangements, the heat transfer efficiency will be more in regenerators. And in the second subdivision is relative to the direction of motion. There are three types of heat exchangers under this. One is parallel flow, counter flow, third one is cross flow. The parallel flow heat exchangers are nothing but, here I am taking this may be a shell, this may be a inner tube, or it can be a concentric tube like this. This is inner tube and this is called as outer tube. Okay, in the inner tube some fluid is flowing, maybe hot fluid is flowing. In the outer tube, maybe cold fluid is flowing. So the same condition I am taking here. I am taking a tube like this, and around the tube there will be a cell like this. The cell input is here and output is here. The tube input is here and output is here. The same diagram I am explained here. The hot fluid is flowing inside the tube and the cold fluid flowing in the cell. Okay, in the cell side, the cold fluid is called as cell side fluid. The hot fluid is called as tube side fluid. Okay, these two fluids will exchange its heat in between them. Once these two flow direction, here if you look at this, the cold fluid comes in this direction and goes in this direction and goes out in this direction. So cold fluid flowing direction is forward, and also in the hot fluid, the hot fluid flowing direction is also in this direction. So both, if hot fluid and cold fluid flows in same direction, then the heat exchanger is called as parallel flow heat exchanger. Similarly, if these two fluids are flowing in opposite direction, then the heat exchanger is called as counter flow heat exchanger. Okay, in the figure 3 here I am giving another interesting example. The hot fluid is flowing inside the tube, okay, where in the cold fluids are flowing in this direction. So perpendicular to each other. Hot fluid and cold fluid are flowing perpendicular to each other. This kind of heat exchangers are called as cross flow heat exchangers. And the third type of classification is design and constructional features. In this type of classification, first one is concentric tube. As I already told you, a tube will be there. Over that, a tube will be there. In the inside cylinder, hot fluid or cold fluid may be flow, and in the outside cylinder, maybe hot fluid or cold fluid may flow. These kind of heat exchangers are called as concentric tubes. Okay. In the next thing, shell and tube heat exchanger. Here I am going to show you the shell and tube type. Here there will be a large shell like this. This is your shell, and inside the shell there will be number of tubes flowing like this. Okay, so inside the tube the hot fluid or cold fluid may be flowing in this direction and it will return in this direction. So the fluid is passed inside the cylinder two times, in the forward one time and in the reverse direction one time. So this is two pass cell. So two pass flow. So here there is only one cell. So this is called as one shell and two pass. In case if you have a cell like this and if you have tubes like this, then it is called as one shell, one pass heat exchangers. Maybe two shells, one pass, two shells, two pass, whatever the combination is possible. Here I am showing you one shell, two pass heat exchangers. Okay, this is called as shell and tube heat exchanger. The third thing is multiple shell and tube passes. I already told you what is multiple shell and tube passes heat exchangers. And the fourth one is compact heat exchangers. In compact heat exchangers are nothing but in the practical conditions, you may see in the modern cars the radiators, the size of the radiators are very small, right? Those radiators are called as compact heat exchangers, where the heat exchanging area is very small but the efficiency of the heat exchanger will be very high. That type of heat exchangers are called as compact heat exchangers. Okay. And the last classification, physical state of fluids. In the physical state of fluids, maybe the physical state may be the fluid may be in the condition of vapor or in the condition of liquid. So this can be classified into condensers and evaporators. In condensers, the vapor is converted into liquid. In evaporators, the liquids are converted into vapor. Okay, here the vapor is losing its heat to the surroundings. In the evaporators, it is gaining its heat from the surroundings. So this is the basic difference between condensers and evaporators. If you look at this, this is the temperature distribution graph of a condenser. In condensers, the hot fluid here, you know that the saturation temperature of water at atmospheric pressure is 100 degrees Celsius. After 100 degrees Celsius, up to 100 degrees Celsius, the heat we are giving is called as sensible heat, and after 100 degrees Celsius, without the rising of temperature, we are giving the latent heat, right? So here the hot fluid temperature may be saturation temperature, and at the exit also the hot fluid temperature will be at saturation temperature. For example, if you take the water as this at the hot fluid here, at the entry condition the temperature of the vapor is 100 degrees Celsius. At the exit condition also the temperature of the vapor will be 100 degree Celsius only. So in between this it will lose its latent heat only to the cold fluid. Here the cold fluid comes at 30 degrees Celsius, maybe I am assuming that the cold fluid comes as 35 degrees Celsius, and it will gain the heat from the hot fluid, that is the latent heat from the hot fluid, and at the exit it may gain the temperature to about 80 degrees Celsius or 70 degrees Celsius. This type of heat exchangers are called as condensers, whereas in evaporators the cold fluid temperature will be same throughout the process and the hot fluid temperature will be reducing along the length of the heat exchangers. Okay, these are all the classification of heat exchangers. Next thing, when we are going to solve the problem, next thing, whenever we are going to solve the problem, we are going to use two methods. One is LMTD method and second one is NTU methods. LMTD method is nothing but logarithmic mean temperature difference method. NTU method is nothing but number of transfer unit methods. Now I am going to derive the expression for LMTD. So del T of LM, logarithmic mean temperature. That expression I am going to derive now for parallel flow and counter flow. So in the first case I am taking parallel flow heat exchangers. Okay, you know that the total amount of heat transferred is equal to UA into del T LM. Q equal to UA del T of LM. Here U is nothing but your overall heat transfer coefficient, area is area of the heat exchanger, del Tm is logarithmic mean temperature difference. Okay, in a heat exchanger the energy released by the hot fluid is received by the cold fluid. If the energy released by the hot fluid is 100 watts and the cold fluid will receive that 100 watts and it will rise its temperature. Okay, so hot fluid, the energy released by the heat released by the hot fluid is equal to heat received by the hot fluid. So here I am writing the equation for the hot fluid, Q equal to m dot h into Cph into Thi minus Th naught, that is entry temperature of hot fluid, exit temperature of the hot fluid. Similarly for cold fluid it is mc into cc. This is mass flow rate of the hot fluid, this is cold mass flow rate of the cold fluid. Okay, these two equations I am taking. In the second condition, so I am explaining all the terms, all the nomenclatures I have given here. So let us consider an element area. So maybe the heat exchanger length may be 1 meter. I am considering only the element area here. In this element area, the amount of heat transfer throughout the length is called as Q, and in case I am considering this as the X length, so here it will be dq. So dq equal to U into, so the same formula I am taking here, U into, similarly area is very small area, so I am taking dA. So dA into T minus capital T minus small t. Capital T is nothing but your hot fluid temperature, cold fluid small t is nothing but your cold fluid temperature. We know the formula Q equal to mCp del T. Okay, the same formula I am writing here, dq equal to m of h. I am considering the hot fluid, mh into Cph into d of T. Okay, this T is hot fluid temperature difference. So similarly dq equal to mc Cpc d small t, cold fluid temperature. Okay, here another important thing another important thing is, in the hot fluid it will lose its heat. So here it will lose the heat. It will, for cold fluid will gain the heat. Okay, so before this formula I am putting minus. So where in cold fluid I am putting plus, because it is gaining the heat, it is losing the heat, so I am putting minus before the formula of hot fluid formula. So I am taking this formula only. I am writing here dq equal to minus mh cph dt. So from this equation I am taking the equation of dt equal to minus dq divided by mh cph. So dt can be written as minus dq divided by ch. This ch is nothing but capacity rate of the hot fluid. Cc is nothing but capacity rate of cold fluid. This can be expressed as mh into cph. This is the capacity rate. Similarly here mc into cpc. Okay. So next thing, similarly I am going to derive another equation for dt from this equation. Okay, that is dq equal to mc cpc dt. From this equation I have to derive the equation for dt equal to dq divided by mc cpc, which is equal to dq divided by mc into cpc is nothing but cc. So I am writing the equation here. Now I am going to subtract these two equations. This is equation number 2 and this is equation number 1. So I am going to subtract these two equations, that is dt capital T minus small dt equal to, so this minus comes from this equation and this minus this one is I am writing here. So dq can be taken out from the equation and inside 1 by ch plus 1 by cc. So now I am going to substitute dq equal to d of ua into t minus t. So q equal to, I already write the formula, no, q equal to ua into t minus t. The same formula I am going to rewrite here. So dq equal to minus ua dA t minus t into 1 by ch 1 by cc. Okay. Similarly here the temperature difference between these two is taken as d theta. Okay. So this t theta equal to this equation, right? So d minus t equal to theta I am writing here. So this has to be substituted here so that the equation becomes minus u into dA theta into this equation comes. Okay. So here I am writing this theta has to be comes to this direction, d theta divided by theta equal to minus u dA 1 by ch. So I am going to integrate this equation. So by integrating this equation we get up to from 1 to 2. Here these values are constant. So dq divided by theta, integration of dq divided by theta is nothing but ln theta. So 1 up to 1 to 2, from 1 to 2, so I am writing here as ln theta 2 minus ln theta 1, which is equal to, here integration of dA is a. Okay, here I am writing a. So this can be written as ln theta 2 divided by theta 1 equal to minus ua within the bracket 1 by ch plus 1 by cc. Okay, we know that the next step, we know that q equal to mh cph t1 minus t2. So here mh cph is nothing but ch. So I am writing q equal to ch into t1 minus t2. So ch equal to q divided by t1 minus t2. Okay. So I am writing 1 by ch equal to, this has to be go up, t1 minus t2 divided by this guy has to come down and q. The same equation similarly for 1 by cc equal to t1 minus t2 divided by q. Here I have to write small t, right? So these two values has to be substituted in this equation. Okay, this equation may be taken as number 3 and these two values has to be substituted in equation number 3. So ln theta 2 minus theta 1 equal to minus ua. I am substituting those two equations here. Okay, so the q value can be taken out commonly and inside the bracket t1 minus t2, t2 minus t1. This q has to be go to this side and q equal to ua minus ua. So this equation divided by the left hand side ln q2 divided by q1. Okay, so I am just rearranging all these values like this. Okay, like this I have rearranged all these equations and here you know that q equal to capital T minus small t. If it is q2 then it is t2 minus small t2. If it is q1 then it is equal to T1 minus small t1. These two equations I am going to substitute it here. This is what your equation. So these two minuses get cancelled. If I rearrange all these equation, these two minuses will come out and these two get cancelled, and you will get the final answer as Q equal to UA del T LM. So for a parallel flow heat exchanger, if you are asked to write the formula for del T LM, logarithmic mean temperature difference, you have to write this equation, right? T1 minus T1 minus T2 minus small t2 divided by ln of this value T1 minus T1 divided by this value T2 minus T2. Okay, this is the equation for logarithmic mean temperature difference for parallel flow heat exchangers. Okay, comparing, this is what I have written here. This formula will be available in your data book at page number 152. Okay, similarly, for the logarithmic mean temperature difference can be derived for counter flow heat exchangers also, right? So I am writing, I derived all the equations for counter flow heat exchangers here. So the same thing will come, dq equal to UA into T minus T Okay, from this derivation, we can know how to derive the counter flow heat exchangers, a logarithmic mean temperature difference for counter flow heat exchangers. Only the minus symbols will be vary from the parallel flow to the counter flow, right? So, and finally, I will derive all the things, and finally, the equation will be there for your del T LM formula, right? For del T MM for counter flow, this is the formula, right? So next thing you are going to see overall heat transfer coefficient for a plane wall. So I am considering a plane wall. Go to the first thing. This is, I am taking a plane wall. Here in the inside of the plane wall, the heat transfer coefficient known as Hi. In the outside, it is known as H0. The length of the plane is known as L, and the thermal conductivity value of the material is known as K. Now, the overall heat transfer coefficient is written by 1 by U equal to, so the outside resistance 1 by H0 plus the conduction resistance L divided by K plus 1 by Hi. This is the equation for 1 by U. So I am rearranging the equation for U. So U equal to 1 divided by hold the bracket 1 by H0 plus L by K plus 1 by Hi. Similarly, for a cylindrical wall condition, you can write the same equation from the plane wall composite cylinder process. This is the equation you can get from the composite cylinder, and this equation can be rearranged like this. Then here it is very important, the temperature distribution in parallel flow heat exchanger and counter flow heat exchanger. Now, as I already told you, consider a concentric tube in which the inside tube has cold fluid and outside tube has hot fluid, right? So the hot fluid will lose its temperature to the cold fluid, right? So consider that hot fluid enters at 80 degrees Celsius and leaves at 30 degrees Celsius, 40 degrees Celsius maybe. So similarly, the cold fluid enters at 20 degrees Celsius and leaves at 35 degree Celsius. So the temperature distribution will be at entry condition, the hot fluid temperature is 80 degrees Celsius. Along the length of the heat exchanger, it will lose its temperature like this. Okay, this is the direction of heat flow. Now, in the entry region, the temperature difference del T of inlet equal to T1 minus small T1. Similarly, in the exit of the heat exchanger, del T at outlet equal to T2 minus T1, T2. Okay, T2 minus small T2. So now the logarithmic temperature del T LM equal to, so the temperature difference in the inside condition is known as del Ti minus the temperature difference in the outside condition is del T naught divided by ln of del Ti divided by del T naught. This is the equation for logarithmic mean temperature for parallel flow heat exchangers. You don't need a data book even to take these formulas for parallel flow heat exchanger. Similarly, in a counter flow heat exchanger, the cold fluid may be flowing in this direction and the hot fluid may flow in opposite direction. If you take the length of the hot fluid enters in here and the cold fluid enters here, right? So in this direction. So if the hot fluid temperature is maybe 80 degrees Celsius and the exit temperature of the hot fluid may be 40 degrees Celsius. Similarly, cold fluid enters from this direction. So here the cold fluid temperature is 20 degrees Celsius and at the exit it is 38 degrees Celsius, right? So now in the entry region del Ti equal to T1 minus T2. Similarly, del T exit equal to, at the exit condition it is capital T2 minus small t1. So now del T Lm equal to del T I minus del T naught divided by ln del T I divided by del T naught. That's all. Okay. So like this you can write the del T Lm formula without using heat and mass transfer data book. Okay. Thank you all. In the next video we will solve some problems on heat exchangers.